first I tried to make this entire video without mirroring the image so that you could read the board. So I feel like a genius. You should too. So what we did in this lab was we took an object, some water, and we put that water inside of a calorimeter cup. So those are going to be the three things that we're going to concern ourselves with mathematically. But how we started this lab was we took a calorimeter cup of a known mass, and we filled it with some water whose mass we also knew. Nah, that's really small. So we've got this guy over here just waiting for us to drop something in, and we also know his initial temperature. And that initial temperature will be the same for the cup and the water inside of the cup, because we're going to leave that system alone long enough that they should reach equilibrium. So we're going to have Ti for that system. Let me get it and write it down, and then I'll get out of the way. A second. Looks like 20.76 degrees Celsius. And that is T sub I sub H2O slash CAL. CAL standing for calorimeter. And from there, we moved on to this big old boiling thing of water, whose mass doesn't matter. Because all that matters is that we get our lovely copper cylinder really hot. So once this water is boiling, it's just boiling water. Boiling water puts off steam, and we'll pretend that's the only time it puts off steam for now. So anyway, we're going to drop this guy in here, and we're just going to leave him there until it's very hot. Hopefully, the exact same temperature as the boiling water. So we measure the temp of the boiling water, and we assume that that's the same temperature as the piece of copper has. So we have the initial temperature for the copper, whose mass we also know, by the way. We know everybody's mass and temperature. So our Ti object was equal to, Ti object is equal to a whopping 98.45 degrees Celsius. And I think you can actually read that. And since we have both of our temps for that, we are going to drop our very hot copper into our calorimeter cup. And we are going to measure the temperature as that reaches equilibrium. And when it does reach equilibrium, that'll mean that all of the things in the system are now the same temperature. And now this system is going to be H2O, a calorimeter cup, and an object, which in our case was a tiny piece of copper. So T final for the entire system, so I'm just going to write T sub F because it's not an easy thing to get confused, was 23.9 degrees Celsius, which seemed really low to me considering that this object was whopping 98.45 degrees Celsius, but Mr. Whipple promised that was okay. So, all those things are super important, but they take up a lot of room on my board right now since I wrote them giant, so we will go back to this big old equation here, which is the entire point of these labs. It's Q total is going to be equal to Q for the entire system, so Q object plus Q water plus Q calorimeter. And it's going to equal 0. And Q, as we got from the notes, if you ever got the notes, Q is MC delta T, where M is mass, C is specific heat, and delta T is, of course, change in temperature in degrees Celsius. So we can sub this all out and make it really complicated. I'm going to do it by color so that it's easier to understand. So I'm going to start with purple, then I'm going to move on to green. Dark enough green that you can kind of see it. Maybe that doesn't look green for you, but anyway, that's what color it is. And blue! Oops. And I'm going to expand this out now. I'm going to stop the camera while I do because it'll take me a second. Alright, I'm going to have to read you the numbers because it doesn't look very clear, at least not in my little screen. So we have 0.0572 kilograms, which is the mass of the object, times 386 joules per kilogram degrees Celsius, which is a specific heat of copper, which we just looked up, times delta T, which is going to be the final temp, 23.9 degrees Celsius, minus the initial temp, the temperature of boiling water, 98.45 degrees Celsius. And then we add to that 0.1581 kilograms, the mass of the water in the calorimeter cup, times 4,180 that is, joules per kilogram degree Celsius, which is the very, very high specific heat of water, times 23.9 degrees Celsius minus 20.76 degrees Celsius, which is delta T for the water in the calorimeter cup. It's also delta T for the calorimeter cup itself. Plus 0.0604 kilograms times the specific heat of the calorimeter cup, which is our unknown in this equation, times 23.9 degrees Celsius minus 20.76 degrees Celsius. And all of this is going to add up to equal 0. So that's how we're going to solve for the calorimeter cup. So I'm going to simplify this right now, and then I will do the algebra. Alright, so there are blurry spots yet again, and I don't know how to fix that, so we're just going to have to deal with it, I guess. But what we have is Q of the object, Q of H2O, plus M delta T times the specific heat of the calorimeter. So to solve for the specific heat of the calorimeter, we are going to add these two up and subtract them from 0, and then we'll divide by this number that is out in front of the specific heat of the calorimeter. So what that will come out to, if I scoot over here to right, you can't see it all, okay, is going to be negative 429.08976. This big mess. There's a decimal point here. So that is, there's also a decimal point here. That is negative 429.08976 over 0.18965, which equals 2262.46 joules per kilogram degrees Celsius. Okay, didn't leave myself enough room to write over here. So that cluster is just kilogram degrees Celsius. So that is actually the answer for this first half of the lab. And we're going to be using that number in part 2 of the lab, where we indirectly measure how hot fire is. And we use the same equation.